I was recently helping a friend work through some cam settings in Fusion, and he suggested I start a quick like Tim's Geek Tips videos. So here we are. Let me know if this is helpful, what you'd like me to cover more in the future, and if you want to see anything specific. So let's get to work. So some of you may have seen this this part in the past. I used to use this as a workshop part because there's a lot of good lessons here. Let's start with where you can find the part. So this part you can find in cam samples. If you go to your data panel, go down to cam samples, under tutorials, it pops up at the top for me. It's called contact point boundary. I went up and did a save as and saved it somewhere local. I've also kind of played with some of these settings and updated it. But I think what we're going to do is we're just going to walk through the part. I'm just going to talk about it. These videos, if I'm going to do a series of them, I want to keep it pretty low key. I'll try to keep it somewhat efficient and drop some little geek tips on you guys. So let's just look at the first setup for this. Nothing revolutionary. This is a face operation. Let's open it up. This only takes like 5 mouse clicks to get a really good face operation if you have your parameters set right. So I didn't select anything in geometry. The real magic on a good face operation is to start the top height at the stock top and to finish the bottom height at the model top. That'll cut everything from the top of the stock to the top of the model. From there, if we go to Passes tab, this is where some of the other magic happens. If we had 2 inches of material and one pass, we would ruin our face mill. So I've gone in here and kind of micromanaged some of these step over settings. If I edit the expression, this is a really good expression. It's basically going to cut 85% of the the bottom flat area of the tool. But then I also turn on multiple depths. And if I look at the expression on multiple depths, it's 40% of the flute length. So anybody not familiar with this, pretty much the weakest part of the insert is right at the set screw. So I like to cut below or above. Doesn't have to be a ton below or a ton above, but so this is just defaulted to 40% of the flute length. I do a finishing step over by default, and then I believe my my finish feed rate is half of the cutting feed rate. You can work that out however you want, and then I'll typically do like a 15 or 30 thou step down. So once you have that, I like to go to save parameters by default. If this is how I'm going to do most of my facing. Now next time when I go to a face operation, I can just pick a tool and hit OK. So it's like 5 mouse clicks and I have a good face operation. So let's move on from some of the boring toolpaths. The conversation I was having with a friend was containing toolpaths, and that's one of the reasons I like to show the first operation here. What we're gonna get into is some cool 3D machining toolpath control, but I want to talk you through some of the ways to control 3D adaptive. So this is a 3D adaptive, even though it looks like just a 2D adaptive. There's some kind of creative geometry selections to get a 2D adaptive at this height. So just wanted to highlight the ability to no geometry selected, and I basically did just the profile by setting the bottom height to 30 thou below the model bottom, and then the top height to model bottom plus 25 thou. So what that does is it gives you this like CAT scan view, right? It gives you this CAT scan view which only shows the profile of that little slice there, or maybe more of like a MRI type view of it. So that's how I got just the profile with the 3D Adaptive. 2D Contour, I think the only thing we want to talk about here is anybody that's not super familiar with geometry selections in Fusion. It is a learned skill. And here, the easiest way would be just grab this profile here. But I wanted to kind of highlight one way to do it would be click here, click again, and that's going to pop up the selection manager. Go to closed contour. If I pick here, it'll start walking its way around, and then it kind of takes the wrong turn there. So I'm just going to go right in front of that, click there, and that'll get us the full profile of the part. And then the heights is going to be set to, you know, the model bottom minus 10,000. So that's how we got that. This is a 2D adaptive. If we look here, I did a geometry selection of the open pocket, and then if I didn't have stock contours turned on, we would get all this extra air cutting out here, because remember, we already machined the outside there. So here, I'm going to turn on stock contours, and I'll select that profile, and that trims it to just the area that I want to machine. I'll regenerate this because this is dependent on that. And then we'll talk about how we controlled another 3D adaptive to just machine these pockets with very little or no geometry selections. A lot of people would get hung up on trying to contain a 3D adaptive toolpath inside of this, where all I really had to do was pick this face as the top, pick this face as the bottom. The only thing it really found, because the stock definition is to only stock you have to machine is the remaining stock, and in between these two heights, that was the only remaining stock to go machine, so I went to machine those. 2D adaptive, it's probably worth remembering or knowing that you can pick contours at different heights, and this we didn't need to go select the stock contours because it just didn't need it. Drills, a pretty boring topic, but this is actually one of the things that came up with a friend I was recently talking to. My heights, the depth of my heights, if I look at an expression here, I must not have, anyways. This is drilling. It's going to drill, it's going to chamfer these holes, and then it's going to tap them. And so let's look at how I would set the depth. So hole bottom, first I selected the walls for the holes. Selecting the walls for the holes helps it find the top and bottom of the hole. And then did same diameter, and then auto merge hole segments. On these holes, it doesn't really do us anything to auto merge the hole segments, but what it does do is if we had a big chamfer or a counterbore, it's going to keep the tip from colliding or having a collision. So if we had a counterbore here, it would make sure we started the cut at the top of the hole. And that's what auto merge hole segments do. That's a nice tool tip for it right there. So on the heights, I almost always do drill tip through bottom. And then for my breakthrough depth, I want to make sure to drill past enough to allow room for the lead in of the tap. So in this, it's going to be a 632 hole. So we're going to do, in parentheses, we'll do 1 divided by 32. I knew that was wrong. 1 divided by 32 because we're doing a 632 hole. And then we'll times that by 4. Actually, I'm going to times that by 5. Your standard tap with no bottom tap or whatever is going to have a four threads as a lead in, as a taper. So you don't get a full thread until you're at about 4 threads. So I'm going to drill past that by 1 thread and hit OK. All right, so then on the chamfer, I'm not using this chamfer tool as a spot drill. Some people might do that, but you're gonna damage your drill. You're gonna have inaccurate holes. You're gonna have all kinds of problems. So this was a 140-degree drill, carbide drill, 3 flute. It's great. I don't need for this hole. I don't need a spot drill for that. And if I did, I would make sure it was a bigger included angle than the drill that I'm using. So on the geometry tab, knowing that this hole was modeled at the major diameter of the hole, I'm going to go down to define my bottom height just with a chamfer width of 10 thou. So that's 10 thou bigger than the major diameter. If I knew the major diameter, maybe I would do chamfer diameter. So whatever the chamfer diameter I wanted to set, maybe 10 thou bigger than the major diameter. But here I'm going to go chamfer width 10 thou and hit OK. So if we zoom in there, you can see of a 10 thou chamfer. And then for the tap, let's set the bottom for the tap of, same thing we're going to do. We're going to do parentheses 1 divided by 32. That'll give us our pitch. We're going to times that by 4.5. And that'll give us just a little past the full thread depth, assuming these were modeled at the full thread requirement. So now what that does is, if well, it's going to create a breakthrough there, so I probably want to rethink that, to be honest. Now what we want to do is we can look at the drill. So the drill and the tap kind of satisfy each other, right? So we'll have to go back and look at the thread depth and all that and make sure we don't get that breakthrough, but we'll push on now because that's just a little nugget I was trying to drop on you. This chamfer is probably worth talking about. I use a 2D contour for closed chamfers. That means not an open contour like this. And then I use the chamfer tool for open chamfers like this. And the reason why is because I like to save my defaults to work with kind of this magical automatic clearance settings. So if we look here, we have a very small clearance there. We're basically getting up to that wall as close as we can. The higher you get up this chamfer mill, the closer you can get to that wall. And that's being driven by this, on the passes tab, there's this chamfer tip offset. If I go look at the expression, my default here is, what I'm doing is I'm taking the tool diameter and dividing that by 2, and then the tool tip diameter and dividing that by 2. So I'm actually subtracting the tool tip diameter from the chamfer area, right? So what I'm doing is I'm getting one side of the chamfer area. And then what I do is I subtract the chamfer width and then subtract this 5 thou. This 5 thou is the amount that the tool was above that surface. Once I do that, I just, I'll come over here and I'll hit save as user default. So next time when I use 2D chamfer, that's in there by default. So now when I change my chamfer size, you'll see this tip offset changes. So I make it 20, that changes. If I make it 10, it changes. So that the very top of the tool is 5 thou above that surface, and then I respect a wall clearance of 2 thou. Now wall clearance should be as accurate as you think you machined this wall. So if I have a plus or minus 1, I'll give it 2 thou. If I have a plus or minus 5, I'd probably give it 6 thou. And that's how you get that real close down there. For closed contours, because I don't want to include those options, I typically do 2D contour. So that's all the boring stuff. Let's get down to the next operation and get a little bit deeper. So that face operation, those 5 mouse clicks, because I had a good default set. When we get in here, this is what I really want to dig into. There's a couple things to really look at here. This 3D adaptive works fine. It's just a few mouse clicks and you have, the whole part, the second half roughed out. If we went and looked at that, on the geometry side, what do we have selected? So we have basically, what we did was I selected the outside contour. I actually did it with the same thing here because I know later I want to add a chamfer here and I didn't want to reselect it. But I used the same profile selection as I did up here. And that's what helped it only machine the area that it's machining now. The heights, I started at the model top because we just faced it, remember? And then the model bottom. So that got me a pretty good toolpath, but I have a lot of reposition moves. And then if I zoom in close, I have what I call ghost cutting kind of in this corner here. So I'm going to explain how to deal with both of those now. First thing we're going to address is this ghost cutting. I call it ghost because it's running around chasing material that doesn't exist. Like it's running around chasing ghosts that don't actually belong there, right? And when we're done with that, we'll look at, this toolpath versus this toolpath. This is what I would probably run out on the machine. It's minute 36 seconds versus 2 minutes 51 seconds. So it's way more efficient. Doing the math, I think we're 40-something% less cycle time to do this one than it is to do this one. So let's chase those ghost cuttings first and try to understand it. So if we hit edit, really the answer is here. So in the tolerance area is how we fix this problem. So let's go look at the next toolpath, and I'm doing this kind of back to back so we can save some watching the toolpath calculate. On the passes, I have this at 3/10. My typical default is to have this around a half a thou. And then if I see some ghost cutting, I'll make it smaller. Often I'll just make it 1/10 if I'm trying to get rid of a ghost cut. And then maybe make it bigger if I'm really trying to optimize things. But what's happening in the background is, and this will make sense, as we're looking at other toolpaths later, is every CAM system I've ever used, and it's probably 7 of them, there's a tessellated model in the background gets created, and it actually gets created based on this tolerance. There's probably some other geeky stuff that I'm unaware of, but and those tessellated kind of triangulated surfaces are what is showing up in these corners. As this toolpath is stepping up, it's analyzing that level and saying, where should I go cut? And with a higher toolpath tolerance, it was finding like remnants in these corners that it had to go machine. So if I made this 3/10 instead of the other one was 4 thou, it cleaned up those ghost cuts in the, some people just call them air cuts in the corner. There's no material there because it machined from the bottom up. So that cleaned that up a lot. While we're here, it's worth talking about a smoothing settings, right? So if I turn off smoothing settings, maybe I'll go speed up this calculation, but we'll watch this calculate for a minute. Okay, now that it's done calculating, you can't really see a difference from what it had before and what it had now. But where you do see it is when I come down to these settings and turn on points, this gives you kind of a view of the code that the machine's going to, or the CAM is going to create. So each one of these black points represents a line of code. And the other thing to look at is when I expand the toolpaths, this is almost 500 kilobytes, this is 850 kilobytes. So there's, this isn't a one-to-one exact replica of how big your G-code program is going to be, but it's actually pretty close. If you cut this to be half of that, the code ends up being how many lines of code, it's pretty similar. So depending on the machine you have, some machines like tons and tons of code. So maybe this is a better program and you'll actually get better machine motion with all this code. The Haas that I have out in the garage is the opposite. If I come down here and turn on smoothing, and there's some misunderstanding about this, if you read the tooltip, what my takeaway is your toolpath tolerance is a combination of your tolerance plus your smoothing settings. So 3/10 plus 1 thou and 2/10 is 1.5 thou. So this toolpath is still less than half of the tolerance. And think about it like a profile of a surface tolerance. Your perfect toolpath is here. You get half of that on one side, half on the other. And that's what your toolpath is going to stay within. So while I'm talking, I'll let that calculate. And then we'll go back and look at the point distribution with that tool. While that's calculating, let's look at this one. You can see all those black dots represents a line of code, and there's a way fewer dots here. That's with a 4 thou tolerance. The other one had a 3/10 tolerance. And so it's done calculating. You can see now we actually have, with a smaller tolerance, a less than half the tolerance of the first toolpath. We actually have a smaller toolpath. So 190 kilobytes, and this is 194. So it's basically the same, but this actually has a better, tighter toolpath tolerance that it can deviate from kind of the perfect toolpath. And then when we click on it, we can see down in the toolpath, you actually have way fewer points. You actually get some more points up here, but that's because some settings that we'll talk about here in a few minutes. But the cutting motion on this, on my Haas machine, is going to be way better than the cutting motion of this. And that's before you get into like the G187, smoothing settings. And then the tool path is basically the same file size. So the next thing to talk about is these settings here. There's a lot less up and down repositioning motion, right? This is kind of up and down. Some people refer to this as like a sewing machine effect because they see the spindle doing a lot of, this up and down sewing machine effect. The column on my machine, my Haas machine, and many other machines, the column's one of the things that actually moves slower than the rest of the machine. A lot of times your bed dynamics are a lot smoother and quicker with your acceleration, deacceleration, than the big column on your machine. Obviously, that's machine specific. Some of the little brothers and robo drills move up and down pretty damn fast. But let's look at the settings that I used to change this. So that's going to be in the linking tab. Think about the linking tab of how you get around the cut from cut to cut. The passes is kind of your cutting parameters. Heights should be pretty self-explanatory. So one thing I changed was I went from full retraction to minimum retraction. And then this is a controversial. I'll suggest you do some testing and understand what's happening with this. But I personally run high feed rate mode. Always use high feed rate is what I select. I choose. A lot of people do preserve rapid motion. This, if you get any dog legs, I think for the sake of this video, we'll suggest you just go learn about dog legs with Google and whatnot. But if you get dog legs with your machine, this is how I fix it with my machine. And then I always set this to basically the fastest my machine will feed. So in these reposition moves, it's feeding at 800 inches a minute. That scares some people. That's kind of the controversy behind it. Allow rapid retracts I leave on. This is another one to gain a lot of efficiency with your 3D Adaptive. Maximum stay down distance. I typically just make this bigger than my part. I don't remember how big this part is. I think it's 4 inches, so I made it 6 inches. So that'll force it to stay down. Some of these moves from here all the way over to here, if I had a smaller stay down distance, maybe half the size of the part or 2/3 of the size of the part, maybe that one would force it to wrap it up and over and down. And then we have a stay down level. So when you have to move up, over, and down, it'll do it. But if you can, it's allowing it to go a further distance with this stay down level. I'd have to go refresh my memory exactly the calculation that's happening, but I believe it actually will let it go 70% more distance than if it went up, over, and down. That seems to be what works best for me, my machine. Every once in a while I'll say most, and I rarely get below 50%. Some people like to leave it on least, so that's something you're going to want to play with yourself. And then again, my no engagement feed rate, that's going from here over to here. That's 800 for my machine. I think my machine maxes out at 833 or something along those lines. So those are the settings that we went from 2 minutes 51 seconds to 1 minute 36 seconds. I may have actually just changed something to make that a little bit faster. I don't know what I changed there, but that's a real significant difference. And I can also say the cutting motion on my machine would be even better. I don't think we need to talk about this. That's pretty straightforward. We did talk about earlier, I believe we talked about trimming to your stock contours. It would cut way out here to the profile of the part if I didn't select this to trim it shorter. Nothing really to see here, or here, or here. So now I want to talk about, I'm going to turn off my show points down here on the view settings. Now I want to talk about containing 3D toolpaths. And I think this surface is a good, simple example of what I see a lot of people struggle with, which is just containing their toolpaths and getting it to go exactly where they want. And one of the bigger reasons, and the reason this part is named contact point boundary, because people don't understand how to use contact point boundary and they don't know what it's actually doing. So what we want to end up is a toolpath basically like this. Maybe we'll play with kind of bending and shaping that toolpath. And then we'll make sure to show you how to do just little segment geometry as well. So let's go up to use a parallel toolpath on this. And so we're learning how to contain 3D toolpaths. This is the thing I see people probably struggle with the most. So we're going to kind of do it layer by layer, which is the way I think and typically the way I learn. So we'll come from selection. And the first thing I want to do is select the outer profile. I could pick here, but I'm going to pick this profile because I'm going to add a little chamfer there later. So I'll pick here. I'm going to select it again. I'm going to redirect it to go the way I want it. So far so good. And then it went inside here. So I'm going to say actually come back outside here. So that got me the outside profile. What happens if I just hit OK? All right. So it machines a bunch of stuff I don't want to machine. So I want to contain that to really just machine here, here, here on both sides, right? So if I come in here and hit edit, I think the next geometry I'll select is this edge here, which means I should do it over here as well. Hit OK. So we're getting closer. Now I don't want it to go in this hole or those holes. So we'll hit geometry, we'll pick here, here, and here. Hit OK. So we're getting pretty close. And this would probably be fine, right? But this is flat, and we already faced that. So let's talk through several options you have to machine only the areas that we want and not machine this surface here. So many people, especially people that had come from other tools, other CAM tools that do a lot of surface selection, would leverage this newer functionality that's in Fusion that I honestly like a lot. It's a tool in the toolbox that I don't use a lot, but it's a powerful tool that's worth knowing how to use. So they come add a surface group, and then maybe they'll just pick this surface here and choose it as an avoid surface, and then you can say axially, I want to avoid it by, let's just make it small, like 1/10,000th of an inch. Now let's hit OK and see what result we get. That looked like it did what we want, right? If I zoom in real close, though, you can see the toolpath actually is coming a bit short of that. And I'm guessing because the Z difference, or the axial difference from here to here, is tiny. It's only 1/10. You see it does come short a bit. Maybe that's totally fine, and I move on. But I'm trying to show you some stuff, right? I was just showing this to a friend, and he was like, man, more people need to know this. So here we are. So let's kill this avoid surface. And maybe another one would be a heights containment. We could define the top as model top minus something small. Probably get about the same result that we got, right? Or maybe exactly the same that we just got. So I don't really want to do that. My go-to here, make that 0. I'm back to machining the whole thing. My go-to here would be a slope containment. We have a horizontal surface, and we don't want to machine it. So what happens if we went to geometry slope containment? Right now, this is saying machine everything from 0 to 90. And this is important to have in your toolbox of stuff you know how to use. I can say actually machine everything from 1/1000th of a degree to 90 degrees, and let's see what that does. So there's 3 different ways to achieve what we're trying to achieve. I'll argue that this is a little better. We're getting our toolpath right up to the point where we want it to machine. So that looks good to me. And it's basically a great looking toolpath. I actually see something I don't like down here, other than it just looks great. Let's do a simulate. Show all toolpaths, no stock. And if you didn't know this tip, it's definitely something you want to have in your toolbox. You can go over these little points, which happen to be your points, in your toolpath, and they'll turn red. And you can put your tool right there. You can come to this back, and looks like my buddy Scott's trying to get a hold of me. And you can see right here, I can left click and hold my left mouse button right in the middle of the screen. I can go back and forth with my cursor and walk it through the toolpath. And you can see what's happening is it's not machining our whole surface. And the center of our tool is going out to the boundary that we gave it, right? So we're actually getting exactly what we asked for. We wanted to machine the whole thing, but we got what we asked for. So let's dig into it a little bit more and then understand that better. So I'm going to right click here, hit edit, and on the geometry tab, tool containment is center on boundary. I see a ton of people have this problem and go straight to outside boundary, start adding a bunch of value here. I can tell you most of the time I'm going to leave this on center, tool center on boundary. So I'll leave that there, and then really what I want to do is add contact point boundary. We're going to add contact point boundary here. Okay, and then I just went and checked something here. Don't worry about that. We'll talk about it later. Then we'll hit OK. And this is scary, right? This looks like we're going to go do bad things. I want to encourage you to look past the waterfalling of the toolpath, and let's go do another simulation and see if we at least, looks like we created a problem, maybe solved a problem and created a problem. So we'll dig into that and understand it. We'll click here. Verification's got an error. It's a nice thing to tell us because we're going to collide down here, right? Well, we fixed this problem, right? It looks like we're actually machining the whole thing. But remember, the center of our tool was supposed to go out to the boundary, the selection that we picked. Now, what does contact point boundary mean? It's the contact point of the tool, which is really anywhere that can cut. So it's going to be from down at the tip all the way up to the top of the flute here. And that's where we're going to understand the waterfall in just a second. But now we can see the contact point of the tool is allowed to go out and cut all the geometry to the boundary that we selected, that geometry boundary, right? Now let's understand this waterfall. What the heck is happening with this waterfall? So what's happening with this waterfall, the answer lies in the toolpath tolerance. So let's go take a look at that. As I mentioned before, in the background, there's a tessellated model that's created at the tolerance of the toolpath tolerance. So there's a bunch of little triangles created, and at a 4/10,000ths toolpath tolerance, there's some little triangles down here that it's finding and it's saying, hey, I can use the whole contact point of the tool to go cut that geometry. This is exactly what it's doing here. So what's the fix is all we should really care about, right? And the fix is, if you come to additional offset, most people think about that as a positive value. And if I made this bigger, we would have more waterfalling. I'll spare you the time of watching my proof of that. But what we really want to do, sometimes you'll see people just come in here and hit -1,000, and that would actually fix it. But a smarter way to fix that is going to be type in negative tolerance. When we hit OK, that's going to clean up our toolpath because it just pulled it in by those little triangulated tessellations that it was finding. And now when we come do a simulation, click on those little points. Now we have our problem solved and no waterfalls. So that's pretty basic, fundamental toolpath containment. I'm going to drop a couple more just fun things on you. This is a great toolpath. A lot of times I just get a successful toolpath and then want to play with others to make it, to play with the cosmetics, right? Anybody that's been using Fusion for a while and used 3D Adaptive, 3D Steep and Shallow, that's probably one of my more commonly used toolpaths because it handles all your steep and shallow surfaces together. Maybe if you're interested, I can do a whole video on different geometry and how different toolpaths work with different geometry. But for now, I'll save you the time. What you didn't see me do here is I got a successful toolpath and I don't want to go through all those steps of recreating it just to see how a different toolpath would look on this surface. So I right-clicked on it, went to Create Derived Operation, 3D Milling, and then I can come pick something I want to try. Maybe Morph would be a good one. Anybody that's used Steep and Shallow for a pretty long time, contact point boundary and kind of getting out to the edge of geometry didn't work really good, to be honest. So I just sent my my old colleagues over at Autodesk an email thanking them for making that better. It works great now. Cosmetically, what I'd like this part to do different or better is I'd like to kind of accentuate this kind of sweep motion here. So I'm going to use a morph and then we'll wrap it up. So ahead of time, I went and created this sketch. You know, I just want to bend and manipulate my toolpath based on a sketch. So I'm going to turn that on. And then I'm going to come to this toolpath. I'm going to go create derive, 3D, and morph toolpath right there. So morph requires, there's lots of content about this, or I think there's lots of content about this. But the nice thing with a derived operation is my geometry is selected. Anything that can transfer over to the new toolpath comes over with it. My slope containment, my contact point boundary settings, my tolerance settings, my geometry, my heights, maybe my scallop height, stuff like that will come over with it. Now all I have to do is a curve selection. So I'll pick this and I'll pick this. And actually I'm gonna back those out. I'm gonna pick this, I'm gonna click it again, I'm gonna pick that right there, and I'll hit OK. Notice that arrow was going that way. I'm gonna pick this, I'm gonna pick it again, and then pick that. Now notice how these arrows are going the opposite directions, and we'll circle back to that in a minute. So what happens when I hit OK? We have an empty toolpath. So I have to figure that out. So let's come here. What happens if I turn that this way? Yeah. So with a morph toolpath, my buddy Rob Lockwood said this one time, and it really connected with me. Those arrows have to be pointing, these guide curves need to be pointing the same direction. Think about what will happen is you'll get a nonsensical toolpath or an error, but it's like taking a napkin and twisting it. That's basically what's happening with the toolpath when they're going opposite directions. So let me just reiterate what I'm talking about there. So in the geometry tab, if you click here, that arrow is pointing this way. If you double click here, that arrow is pointing this way. That's what I changed. I clicked that red arrow and I flipped it to where both arrows were pointing the same direction. I would have, to be honest, I would have done that because I saw it happen. I would have done that before looking at the toolpath. But check out this morph toolpath. This toolpath is now arcing more with the geometry. The light will kind of pick up and accentuate that geometry better. Down here, it kind of pinches in, so that'll accentuate your geometry. If this is like a consumer goods part, that's going to be pretty nice. And you can also take, this is a non-parametric sketch, which you'll very rarely see me do unless I'm doing something like just playing with this. I can come back here and I can kind of pinch that down a little bit more. I can pinch this down a little bit more. and then come back and regenerate that toolpath down here. Yeah, you can see that gave us a little bit more pinch in the toolpath. I probably wouldn't use this, but I just wanted to show you kind of a way to manipulate toolpaths. And with that, I've probably gone on long enough. Leave a comment. Tell me if you like this kind of content, if I should do it more, if I should blab a little bit less, or if there's anything specific that you would like to dig into. And with that, I think what we'll show next is this part going through Toolpath.